Well, we're moving right along here and coming close to the end. I do have a couple announcements for you as well as we set up the rest of the this week and next week and then finals week. It's hard to believe it came so quickly on such short notice, and we got a lot to do, but I guess we won't quite get to it. But as you know, we've been working through and we've got one more chapter to look at. It is chapter 12. It's a short chapter. Saved it for today with the idea that you'll see that I'll start and I'll probably talk about the chapter for about 10 minutes, and that's about it, and then dive into the problems. I think you might recall me telling you on Monday of last week that we would do no new physics between now and the test, and so hopefully that's what it's been working out. Don said a lot of people showed up at the review yesterday, and that went really well. So hopefully those of you who did make it, it was useful to you. And as you know, then other than today, which will be the lecture on chapter 12, and like I said, we'll just do more calculations on torques, and really torques that show up the most. We have a lab today then on static equilibrium on this chapter, and then you have a test on it on Wednesday, and that's probably where you should stay focused, but just throwing that into next week. Next week then we just have 2 lectures left. And unfortunately, that probably means we're going to shortchange the last chapter a little too much, but we will go into 13 and be able to cover 13 quite well, but 14 will get shortchanged a little bit.
So we're not going to do 14, or what is it?
I would say at this point we're probably going to do about half of 14. Hopefully it'll be about half. Might even be less than that. We'll see how it goes. It is, again, not a surprise. It is the chapter that we've kind of designed that way. But there is a point I should mention. Next Monday, a little bit different because I have a couple of important meetings that couldn't get accomplished last week, or it looks like unlikely this week, and so it's going to carry over into Monday afternoon. So next Monday, we're not going to have the lab. That would be the lab on the chapter 14, and so that's going to tie together here. So I'll probably do the lab in class is what we will do, but there'll be no lab that afternoon. So I was talking with Don about it this morning, and he said, now that might be better anyways, because he would then set up the afternoon for anybody who wants to talk to him on Monday as you guys start reviewing for the exam, which is then the following Monday. So we'll leave it then just kind of as an open lab, and so no formal lab, nothing we're going to require you to do. But if you are far enough in your schedule next Monday and you want to do some reviewing for the final exam, take advantage of that. So that'll be what Monday will be.
So you're going to be in the lab reviewing for the final
right. I should check with him. He didn't say it was going to be like one of the formal one like he did yesterday, but one that if people have some specific questions, so just leave it as an open lab. And so I'll run off to my meetings, and he's just going to have the open lab, and he's going to say, come on in, and that would be a good time to ask questions. And I'll be back and forth between 2 meetings, so I too would be around to answer some questions. So anyways, we were talking about it this morning and thought that would be better than trying to fit in a lab that we may not actually cover the chapter with, but help you get ready for the final exam on Monday. All right, so lecture today, test on Wednesday. Next Monday, a lecture on 13, and then next Wednesday, 13-ish, maybe even into 14. We'll have to see how the next 2 weeks play out. But that's the end of the semester. And no formal lab on Monday, but an open lab on Monday. And then your final exam the following Monday after that. So that's only 2 weeks away, and as you know. And I should keep reminding you, where is your final exam?
here at 8.
Here. What time? 8 o'clock. That's the important one. 8 o'clock. So make sure you show up Monday morning, early. All right. Well, with all that said, there's a quick few things I want to show you and then just jump into examples. As I said last Monday, what's kind of neat here is that once we got done with Monday's lecture where we did conservation of angular momentum, everything else was just examples of calculations. And so I did that for you on Wednesday. A lot of calculations looking at conservation of angular momentum. In fact, one of the hard ones was that wheel that was spinning we set down at the end. Another one was that bullet going into the block and tipping it over. And then we had other collision ones that I think were a little bit easier. But we did all those on Wednesday. I would assume you took advantage of Friday's MC and also Sunday's MC. And same thing here, except now we get into chapter 12 here. And chapter 12, as I said, has no new pieces of physics. But it does say about this question here, it throws out a word called static equilibrium. And you might even be able to guess, I'm kind of even hoping you gave this chapter a good look, knowing that there would be a short time frame between this chapter and the test. But what do you think is meant by the word static? Okay, so not moving, fair enough. How would you translate that into mathematics? How would you describe something that's not moving? So what's zero? Yeah, the velocity is zero, right? But that's not it. What else would you do? I think that's the obvious one. Any other?
Conservation.
And that's what I wanted to point out. Now that we've got our objects that have size, when you say it's not moving, you mean it's not translating and not rotating, both of those together, right? So that's what's meant by static equilibrium. So that's what this whole chapter is. This whole chapter is to look at scenarios where we have static equilibrium. Static meaning it's not moving. For example, this would be a good example of a bridge. If you build a bridge, what do you want? You want it static, right? You don't want the bridge to move. You don't want that bridge sitting over the river to move to the left or to the right. You don't want it to go forward or back. You don't want it to go up, and you don't want it to go down. And in addition to that, you don't want it to rotate, right? You don't want it to sit there and rotate. That's not going to do you any good either. Rotate around any axis, all right? So translation or rotation around any axis, it should be zero. So bridges are good examples of that. Buildings are good examples of that. Signs that hang and, are good examples of that. And so different scenarios are good examples of static equilibrium, okay? And in fact, many of you will go on next fall and take what we call our statics class, where you spend the whole class building bridges and building buildings and talking about all the forces that are going on in such that all the forces come out so that you don't have it move. Okay? And so that's what this word static is. Now, in addition to that, we've got this whole idea of equilibrium. And the idea of the equilibrium here is not only are we trying to say that the object is stationary, but it's going to remain stationary. And that's what equilibrium means. In other words, if I were to take this pin and throw it up, at the very top, right here, what's its speed? Zero. What's its acceleration? 9.8, right? It's not zero, right? When it gets right to the top, it's still changing its speed. It always has an acceleration of 9.8. So I would not call the very top a static equilibrium. It's static at that moment, but it is quickly changing, okay? And so static equilibrium means this. It means your acceleration is zero, both translational and angular acceleration, and it remains that way. So, again, taking the physics we already know, if you were to look at the sum of all the forces, that is, if you were to look at the net force, what do you get? Zero, right? Because what we learned back in chapter 5 is the sum of all the forces equal mass times acceleration. And if we narrow that focus to an acceleration of zero, then all the forces have to add up to zero. And so your author calls this condition number 1. If you've got a chance to look at the book right here in the first section, chapter 12, section 1, 12.1, he says condition number 1, sum of all the forces have to be 0. So we'll take advantage of that. If something is going to be static equilibrium, if you're going to build a bridge that is not going to go down or up or left or right or forward or back, then you know that all the forces on the bridge come out to be 0. Okay? That's the requirement. And then, of course, by extension of that, what would you say about the sum of all the torques? Yeah, that would have to be 0 also. So, again, if you got a chance to look, section 12.1 says the same thing. It says, look, there are 2 conditions that are required for an object to be in static equilibrium. And there they are. And so, like I said, these 2, I'll put a little box around it, but I'm hoping these are not a big surprise. This is our torques, this is our chapter 10, and this is our chapter 5. We'll just put the 2 together and say special case at equilibrium. Okay, and that's why I said no new physics. And so we already knew that coming in. And like I said, it's condition 1 and condition 2. And here's what you'll see. Everything in this problem, everything in this chapter, every problem in this chapter is about this. That, hey, we'll set up the bridges, or we'll set up the cables, or we'll set up the rods, or we'll set up whatever. And if it is in static equilibrium, what do you know about the sum of all the forces? 0. What do you know about the sum of all the torques? 0. In fact, this one could be extended one thought further. That means then that if I take an object like this, and I look at the force, let's say there's some force on it, F1, and maybe over here there's something else pulling on it, force F2. And of course, let's not forget that there undoubtedly is a center of mass, so maybe that's force number 3. And then maybe over here there's something else pulling on it, force number 4. And so you put these forces together, F1 plus F2 plus mg in the negative j hat direction plus F4. And you add them all together, what do you get? 0, right? That's all I'm saying. And so this is the same as that statement. I'm just trying to make this lecture at least 10 minutes long so you feel like you get something out of this chapter. Okay? But really, it is no new piece of physics. That's why, again, the best thing I can do is just jump into examples and show you examples. And so that's all your author is doing here. He just says, look, these are the 2 conditions. This is exactly what section 1 and section 2 are all about. And then he starts giving you some examples. And that's, again, what I'm gonna do. He does take a moment in section 2 to talk about center of mass again. But again, we did that in chapter 9. But why would he talk about center of mass again? Because look at what happens when you go to calculate the sum of the torques. This one here is the sum of the forces. But when you go to calculate the sum of the torques, isn't part of calculating torque knowing where the force is? Because don't you always have to calculate torque about an axis? All right, so you need to know where that force is, which is hence why you need to know where the center of mass is, because the center of mass is going to be one of those. So when we were working on this problem, or if we were working on this problem, I would have to pick about what axis. I know the sum of the torque has to be 0, but I should ask you, about what axis? Center of mass. Center of mass? And the answer is any axis. Do you want this thing to rotate around any axis? No. So pick one, anyone. You said center of mass. Great. What do you know about some of the torques around center of mass? 0. It's not supposed to rotate around center of mass. But pick another one. Maybe you want to pick that edge right there. What do you know about some of the torques around that edge? 0. It doesn't rotate around that edge. What do you know about the sum of the torques around that edge, or that point, or that edge, or that point, or over here? What do you know about some of the torques around any axis? 0, right. So take advantage of that. Knowing that the sum of the torques is 0, not just around any axis, but about all axes. Because again, it doesn't do any good to say, well, the bridge doesn't rotate around this one, but it does around this one. No, we don't want that bridge to rotate around any axis, right? And so that's what the condition is. The condition for static equilibrium is that the torques will be 0. Not just around one axis, but around every axis. So there's a lot of equations we can get out of this. And so that we will take advantage of. We will take the torque around this axis and that axis and that axis. Which is why I like the lab today. The lab really emphasized that. You have an object, and you end up doing exactly what's shown here. Now, you don't hang it vertically, so there is no force of gravity. But what you are asked to do in today's lab is you are asked to tie 3 strings to it. So like in this picture. And you are to tie the 3 strings, and you are to design it so that it doesn't rotate on you. And then you, from that, measure the torques. And then from that, you add up the torques. And you come up with 0, or at least close to 0. Obviously, there's going to be some experimental error that your partner is going to foul up on. So you get it close to 0. But it's the second part that I think is really nice. And once you do that, your author says, okay, did you get 0 for your torque? And you're supposed to say yes. And then the next one says, go ahead and calculate the torque around some other point. To emphasize that, pick another point. So maybe you pick the center of the object, which most students do the first time. They take the center of the object and they go, let's calculate its torque. And that seems reasonable. But then they jump on and they say, well, do it some other point. And then they pick maybe over on the edge, or maybe they pick where one of the strings is tied to. And which is fine. But it emphasizes the point that, hey, you got 0 around one point, try a different one. And you try a different one, and sure enough, you measure all the torques, you add them up, and you come up with 0 again. Okay? And fortunately, the author doesn't ask you to keep doing it around every point. And he just does it twice to emphasize, hey, you've done it twice. He does ask you to set it up again, and this time tie 4 strings on it and do the same thing. Calculate the torque around one axis, and you notice it's 0, and then calculate the torque around another 4. And so that's what we'll be doing in a few hours here in the lab today here. But just kind of writing this out then, this would be, of course, then an R1 cross an F1 plus an R2 cross an F2 plus I'll call it R3, and then the force of gravity, mg j hat there for that one, and then the fourth one. And so there's your 4 torques, and you were to add them up and come out with 0. And so, like I said, this is section 1 of the book. Section 2 is, let's look at center of gravity again. All right. Section 3 is let's do a bunch of examples. Now, section 4, and the last one, like I said, a short chapter, there is something I should probably point out. And he does something like this. He says, now, let's look a little bit closer at objects that can apply a force. And he starts off with something flexible. I have a little rope here, but I hope you'll see that whether I take a string or a rope, it's really going to be the same thing. Or maybe a metal cable or a chain. But as long as it's flexible, watch what happens if I were to come over to here, let's say, and say, you know what, I'm going to look at this and say, I'm going to tie this on so that I could put a force on that sink. Okay? Let's look at how this rope, this string, a cable, a chain, but something that's flexible, let's see how it could put a force on this. I mean, could I pull on it? Oh yeah, I could pull pretty hard probably, right? And so when I pull it in this way, I can apply a force. And we've been calling that the tension, right? And we still will. Okay, so I can apply a tensional force on this. Could I push? You see how it's not going to work for a push? We call that a compression. We push inward. So could we apply tension? Yeah. Could I apply a compression? No. So something flexible couldn't do that. But what if it wasn't flexible? What if it was something like this, a nice rigid rod that fit in here and bolted into place? Could I pull on it? Could I push on it? Yeah, okay. So we want to keep that in mind, because when we see something that is flexible like this, we know it's pulling in the direction of the string. When we see something that's rigid, do we know if it's pulling or compressing? Yeah, we don't. It could do both. And it gets a little worse. Let's take this string again. Okay, now I can pull on it, tension, but I can't compress. Okay, could I push it sideways? I really can't, unless of course I wind up the string to the point that I'm pulling it again. So I can do tension again. But can I push it that way? I can't, can I? Darn. Could I do that with this? Yeah, if this was logged inside here and bolted, I could hold it into place, but I could push on it that way, right? I could put a force that is different than the direction of the rod itself. And so the sideways is called a shear. Okay? So a rigid rod is a bit more complicated in the sense that if this is the object and I put a rope versus putting a rod, do you know the direction of the force from this rope? No doubt about it. Same direction as the rope. Do you know the direction of the force from the rod? Now, it could be something like this, couldn't it? So the direction of the force is not necessarily the direction of the physical part of the rod. Okay? And so that's what we need to be careful about here. But I think because we've done it so much for the rope, it's so easy to jump down here and say, well, you have a rod, and you know the angle of the rod, but that doesn't mean you know the angle of the force. Because this could be a lot of different pieces. It could be as simple as pushing the rod straight in. It could be as simple as pulling the rod straight out, but it could be a combination of pushing the rod in and twisting, and so it could be like that, or it could be like that, or it could be as I drawn in the first one, or who knows. We just don't know the direction of the force when the connecting pieces is rigid, because it can push in all kinds of direction. So that's what we want to watch out for as we set it up. All right, well, as I said, I tried to extend the lecture for 10 minutes, and other than my 5-minute introduction, I got that, right? All right, good. So I feel like you got your money's worth. I guess next semester I'll have to do it a little bit longer, because I think tuition's going up, so if people can get their money's worth, we'll have to talk a little bit longer. But that is the whole chapter in a nutshell. So I think the best thing to do is just examples. They not just examples that show you static equilibrium, but because we're talking about forces and torques, it makes a nice review of the last chapters that we did here, and so we can tie it all together. So let's start with one that is relatively straightforward. I call it the bear trap. You'll see why here in number 37. It's maybe a little trap to capture a bear, although I'm not sure how you would actually do this in the wilderness, but that's besides. I guess it has to be a Yogi Bear, because we need a building here. We need the bear to be in the city so we can have a tall building next to it. But anyways, it says here, a hungry bear that weighs 700 newtons walks out on a beam in an attempt to retrieve a basket of food at the end of the beam. Okay? Now I'll pause there, but and draw the picture here. Here's the wall, if you will, which to me it looks like a building. I don't know, I suppose it could be the edge of a cliff. And then it has this overhang, and so this is the main part. And then what they've done is they've put a metal bar, or at least some kind of rigid rod. We don't really know if it's metal, does it? It just says a beam. But here it is. The beam is hanging out here. But I want to talk about this part of the picture. What they're trying to do in this diagram is say that the end of the rod has, like a metal cylinder shoved through it. We call it a pin. And in other words, the metal rod can rotate, something like this. If I were to put this on the edge here, and I were to put a nail through the end, then this rod can pivot. Okay? And so this rod can pivot. Now it doesn't pivot because they have in the picture a cable that is tied up to the ceiling or whatever that overhang is at 60 degrees. And then the bear is somewhere, oh, I won't even try to draw a bear. I'll just do that. Okay, so the bear is somewhere out towards the edge of the food, and the food is then hanging down in a basket down here, and so there's all these goodies down here in the basket. So I'll start again. A hungry bear weighing 700 newtons. So here's the bear, 700 newtons. Walks out on a beam in an attempt to retrieve a basket of food hanging at the end of the beam. The beam is uniform and weighs 200 newtons. All right, so we know the beam has a weight, 200 newtons. It is 6 meters long. So there's my 6 meters. And the basket weighs 80 newtons. A, draw the free body diagram of the beam. Well, I'm glad they said that, kind of. But wouldn't you do that anyways? I mean, that's the whole thing we've been saying here. Look at the forces, and from the forces you're going to get net force, which we're going to set equal to 0 if the beam doesn't fall, if the beam doesn't break, and we're going to get the torque. So, first thing to do in any problem like this, as we're looking at the motion of the beam, is to draw just the beam by itself. So no pin, no bear, no basket of food, no cables, except on that beam there are forces. All right, so what are the forces on this beam? Tension from? I see 2 cables. Okay, so both cables, right? All right. So I'll start with this one and say, do we know the direction of the force? Do we? Isn't it the direction of the cable? Okay, so the cable is pointing down, and so we definitely know the direction of that force. And I claim we know its value is 80. Why? No, I said the way the food is 80. I didn't say the force of the cable is 80. Okay, yeah, if we took a moment to do a free body diagram for the food basket over here. Here's the food basket. Gravity is pulling it down with 80, so how much is the tension pulling up? Yeah, it's got to be 82. Why? Okay, it too is in static equilibrium, and the sum of all these forces have to be 0. So there's a little subtlety in there, and obviously it does come out to be 80, but don't overlook that. There's sound logic behind it. We don't assume anything. There's sound logic there, and if you think you're assuming something along the way, it probably means you're not getting something. You're not thinking through how it's supposed to be set up. But yeah, it is 80. All right, so the basket of food is pulling straight down. It's pulling with a value of 80. Now the other one you told me was the other tension from the other cable. Do we know the direction of it? Yeah, what direction is it? 60 degrees. That was my whole argument of this rope, this something flexible here, is that when you have something flexible, you know it can't compress, and you know it can't shear, you know it only can have tension. So sure enough, we know that. And that one we don't know its value. So I'm just going to put that. So good, you've seen the first 2 forces. Any other forces on here? Okay, the bear itself. All right. So the bear is pushing down. How much? Okay, good. So it's 700 newtons again, because we would go through the same little free body diagram for the bear and say, look, the bear is being pulled down by 700 due to gravity, so the beam must be lifting up. So the beam is putting a force up on the bear, so the bear is putting a force down on the beam, and it would be the equal and opposite. And they have to be equal because the bear is not accelerating up and down. If the bear was accelerating up and down, then the force the bear is putting would be something different than 700, even though the bear still weighs 700. So if this thing was in the process of falling, in other words, this upward force would be less than 700. That's why the bear is falling. And if that upward force is less than 700, the equal and opposite on the beam would be less than 700. But it's not. It is static equilibrium. That's why the static problems are so much more easier than the dynamics problem. But there's my 700. So good. I heard somebody say the bear. And early on I heard somebody say of the beam. Okay, the weight of the beam. And so they did say it is 200. And this is the added piece. Where do I put that 200? Right, and so we go back to chapter 9. That's what the center of mass is. And so the reason they said a uniform beam is so it wouldn't take you too much work to figure out where is the center of mass. Yeah, right at the center of the beam here. So I will put it right there and say there is a 200 Newton force right at the center of the beam. And so this distance is 3 meters. Now I guess I didn't show it in the diagram, but they said that the bear is a distance x out. So I guess I should put x for the distance to the 700 out. They don't give us a number. And at this point they just say draw the free body diagram. All right, am I done? All the forces?
What about the force on the bolt?
Yeah, see, I'm not done, right? Isn't the rod itself being attached to this, whatever this structure is over here? So isn't there a force here? Yeah. And what direction is it? The beam's rigid, right? So do I know when I take something rigid like this and apply it here, do I know the force on the beam is the direction of the beam? No. So what direction is it? I really don't know, right? Now before I put it in my free body diagram, let me draw it over here. So it may be looking something like this. I would suspect, just a purely guess, I don't even know if this is right, but it kind of appears to me with this cable pulling like this, I would think that this whole thing would kind of be shoving in here. In other words, this force probably has to look something like that. Fair enough? Meaning it's got to be pushing back on the beam, because if it wasn't doing that, the beam would move this way. Okay. And also, I would suspect that if it wasn't also lifting up a little bit, that the beam would fall. Okay. And so I kind of suspect that is what the beam is doing. But again, I want to emphasize, notice that the force is not in the direction of the beam. I'm not saying it is. In fact, here's how I'm going to address that mathematically. I'm going to come over here and put it in my free body diagram, and I'm going to label it as a force in the x direction and a force in the y direction. Does that make sense? And that's probably the best way, as you'll see, to handle it, is to look at the components of that force. And I wanted to emphasize that because I didn't want you to think that I was drawing two forces here. These are the two components of the one force. There is a force on that beam, and that force is not necessarily in the direction of the beam. That's why I give it an upward, and that's why I give it a horizontal. Okay, so now I think I've got all the forces. I've got everything touching it. That side is being touched, that's being touched, that's being touched, that's being touched, and then I got gravity. So there are all the forces. So there's step one, free body diagram. And that's what they asked for. And that's what I wanted to show you first. Draw the free body diagram. B then says when the bear is 1 meter out, that is when x equals to 1 meter, find the tension in the wire and the components of the force exerted by the wall on the left end of the beam. Okay, so B is asking for three things, right? It's asking for what is the tension in this cable and what are the components of the force on the beam on the left end of the beam from this wall over there. Okay? So 3 things. 1, 2, 3. But hopefully those 3 things don't surprise me, because I can easily write down 3 equations. What do I know about the sum of all the forces in the x direction? Yeah. That's what this whole chapter is about. Why do I know they come out to be 0? Static equilibrium, right? If it wasn't 0, in other words, that means it would have an acceleration, and that means the beam would be moving in the x direction. So there's condition, I'll say number 1, but it's really number 1, part 1, because also, what do we know about the forces in the y direction? Yeah, that has to be 0 also, because again, if it wasn't, that means you would have an acceleration in the y direction and the beam would be moving. And so that's what your author called condition number 1. These 2 things have to be true. But also the second thing has to be true. What do you know about the sum of all the torques? Yeah, and I'll put torques on the z-axis because, as you can see, a bunch of forces in an xy plane, so calling the whiteboard the xy plane, these forces have a tendency to rotate it either counterclockwise or clockwise, and so it's a z rotation. But I want them to come out to be such that the torque is what? 0. And so those are our 2 conditions. Condition 1, that it does not move with translational motion. Condition number 2, it does not move with a rotation. And so those are our 3 equations. We got 3 unknowns, 3 equations. What could be better? Right? And that's exactly how we're gonna set it up. We don't know that, we don't know that, and we don't know that. Now, even though I've only written 3, and I could stop right there, I bet I could have written more, because I'll ask it again. It's the sum of the torques about what axis? Any axis. So couldn't I do the left? Couldn't I do the right? Couldn't I do the middle? Couldn't I do halfway in between? How many equations you want? I can give you an infinite number of equations, right? Because I know that the torques add up to 0 around any axis. Now I will say that doesn't necessarily mean that they are all independent equations. Because obviously if you have an infinite number of equations that are independent, you can solve for an infinite number of unknowns. And it's not quite that simple. So once we have the torque around one axis, to say the other axis may not be an independent equation. But without worrying about multiple axes, I could just say around any axis. More on that in a minute. But let's go back to the easier stuff, chapter 5. All right, let's add up the forces in the x direction. So looking at my free body diagram, I would say, all right, what forces do I have in the x direction? All right, well, certainly one of them is fx. That's not an x direction. That has nothing in the x direction. That has nothing in the x direction. That has nothing in the... This one does. How much is that one in the x direction? Yeah, there's the magnitude. There's the component. And there's the direction. And so you might call that equation number 1. Now you can't solve it by itself because it has 2 unknowns. But it's 2 of the 3 we are looking for. We're looking for the tension and we're looking for the components. And there's Fx. And that is equal to 0. So by itself, it's useless. But let me move to the other equations. Let's do the sum of the forces in the y direction. So same idea. Sum of the forces in the y direction, this is Fy. That has an x. Oh, this is in a y direction. Right? That's the weight of the bear. That's minus 700. Then we've got the beam. That's another y direction, minus 200. No, then we've got the basket. That's another negative 80. And then we do have a component from that tension. What is it? T, yeah, sine of 60 degrees in the positive direction. And if we simplify that a little bit, we get Fy, and we can put this together. That's 980, so minus 980 newtons plus T sine of 60 degrees. So I'll call this equation number 2. But again, it has 2 unknowns in it too. It has the tension T and it has Fy. And even if I look at these two equations as they stand right now, that would be the total of three unknowns, fx, fy, and t. So these two by themselves certainly aren't enough to solve the problem yet. But again, that's why we can go to the torques. And it would have been nice if I didn't have to go that far, I suppose. But then again, it wouldn't be in this section. I mean, that's what we're learning. This would have been way back in chapter 5, because that's all that was. But now we can get to the torques that we've learned starting in chapter 10, 11, and then continuing here into chapter 12. Let's calculate the torques. And this is what I was saying earlier. Torques around what axis? Any one you want, right? So I would suggest picking one that's going to help you the most. Now, what do you mean by one that might help you the most? Well, this little pin right here, how much torque would you get from these two unknown forces? 0, right? So when we write out an equation, when we calculate the torque around this axis, these aren't even going to show up in the equation, right? The only thing that would show up in the equation is the t. And so I would say that is going to be a good choice here, because we're going to get an equation with only one unknown in it. And isn't it great to have one equation with one unknown? Yeah, much easier. Now, don't get me wrong, you can do any axis you want. So if you want to pick the center of mass, you're more than welcome to. Don't encourage it, but you're more than welcome to. You're just going to have two unknowns in that equation. I mean, one thing nice about the center of mass is this one still gives you 0 torque, because the angle is 180 degrees. But that one won't, and that one won't. So you would have two unknowns in that equation. And so then you would have to put two equations together with two unknowns, which again is not unreasonable. I know you can do that, but it would be nicer if we had one equation, one unknown. So a wise choice here can save us a little bit of extra work. And so let's do that. Let me put it in blue here and say, let's calculate the torque. Let's call this point A here. And so I'm really calculating the torque on the z-axis about the point A, as opposed to the center or as opposed to the right-hand side of it. All right. Now, once I do that, I can calculate my torques. So going down the list here, as you already said, but it's worth asking again, how much torque do you get around point A from Fy and Fx? 0. Why? Because R is 0, right? Torque is R cross F. And you're supposed to take R being the distance from the axis to that force, which in this case, that distance is 0. So for each of these, you get a 0 torque. But now we can go on to the bear. How do I get the torque from the bear?
700 x.
Okay. Okay, so this means when you go to calculate the torque, and I'll just talk about the magnitude, it is a vector, and I'll have to put the vector in there. But didn't we say it was RF times the sine of the angle between them? Well, good. So let me start with the R. What is R? Okay, it's X, but I should have said that they, I'll say it again in B. It says here, when the bear is 1 meter out, okay, so X is 1 meter. All right, so there's 1. The force is 700. The angle is, good, 90 degrees. And there's the torque from the bear. At least that's the magnitude of the torque. What direction is it? Yeah, it's a clockwise rotation, right? And if you want to call that positive or negative, we can decide. Traditionally, we call that negative, so I'll stick to that. But if you take your right hand, this would be R, this would be F, and you'd get into the board. So I would put a negative for the direction. There's the R, there's the F, there's the angle, and there's the direction. All right, you gonna say something?
I was wondering about the 1, but the book gave it to you, right?
Yeah, so the book gives us the 1 now. Going to change that and see. Because the bear's walking out. So at some instant it's 1, but then It's going to be 1.5, 2, 3, 4 as the bear walks out. Okay. So there's the torque from the bear. Let's go on. There's other forces here. The other force here is the weight of the beam itself. Do you get any torque from that? Sure, so let's calculate that. How are you going to calculate the torque? Okay, good, same idea. So it's R. What's R this time? 3 meters, right? And so that's why I was saying earlier, it's important we know where the center of mass is because we have to calculate the torque. And so the center of mass becomes an important step. That's why your author goes through that in section 2. He says, let's review center of mass here. So the distance is 3. What's the force? 200 newtons. What's the angle? 90 degrees. Good. What's the direction? Yeah, and that one's negative too. They're both pushing this beam in what you would call a negative rotation, a clockwise direction. Or if you use your right-hand rule, you got R cross F, and your thumb points into the board. So both of these make it rotate into the board. Let's keep going. We got the basket of food. What is R for the basket of food? Yeah, it's all the way at the end, so it's 6 meters. What's F for the basket of food? 80 newtons. What's the angle for the basket of food? 90 degrees. What direction is it? Negative also. So all three of these are really kind of doing the same idea in terms of torque. All of them are making it rotate downward, right? All of them are making it rotate in a clockwise direction.
So we're like thinking of the rod as having no like height, right?
Yeah. You mean because there would be a slight angle where it's tied there versus the center of it? Yeah. And I think that's the subtlety of that word rod. Going back to chapter 10, a rod we just treated as something that has no height or thickness. It's just one-dimensional. Yeah. Okay, and then finally, we have one more torque to add to this, which comes from that last piece of string or cable or rope, whatever this is, that is tied up to the top. So, what is R for that one? 6 meters. What is F? Okay, that's the unknown, right? T. Yep, that's the one we're trying to find right there. What's the angle? Okay, good. Sine of 60 degrees between them. And what is the direction? And this is a positive rotation. Again, if you want to look at the physical picture, you can kind of see that this cable or this rope pulling up tends to make the rod rotate this way. So if there was nothing pulling it down, that tension would pull it a positive rotation. Or, using your right-hand rule, take your right hand. R is out that way, so I'll put my fingers out that way. But adjust your hand so you can close it towards the force. So which way is my thumb? In the positive direction, out of the board. So a negative rotation, a negative rotation, a negative rotation, and a positive rotation comes out to be 0. Obviously, we better get a positive one on that last one. We can't have all negatives and come out to be 0. So we've got to have negative, 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 positive in order for it to come out to be 0. So it's a longer equation, but the nice thing about it is one unknown. So let's solve this one here. So I will put a 0. I'll get my calculator out here and say, all right, what is the torque calculated by each of these? Now I guess the first one is 1 times 700, so that's a negative 700, and I should have put in my units here. That's a meter, that's a newton. So we've got negative 700 newton meters. This is a negative 600 newton meters. This is negative 480 newton meters. And then this is the 6 meters times the unknown t times the sine of 60 degrees. And so, to get the unknown t, What do I get? That's a 1,780. So 1,780 Newton meters is what these three come out to be, negative until I move it to the other side. Then when I divide it by 6 meters and divide it by sine of 60 degrees, I will get my tension in units of a Newton. And so 1780 divided by 6, that result divided by the sine of 60 degrees comes out to be 340, and I'll round it up, 3 newtons. And so there's the tension in the cable. And if that made sense to you, hopefully, then all the problems in there, because it's exactly the same thing throughout this entire chapter. Any static equilibrium problem is exactly that. The only thing I think that makes static equilibrium problems kind of hard is that sometimes there's just a lot of forces, you know, and there's 5, 6, 7, 8 forces involved here. And so it's kind of long. And then, of course, you could have ended up with 3 equations, 3 unknowns, or 4 equations, 4 unknowns. And so you could have a whole system of equations, but that's more of the math than it is the physics. So the math tends to be a little bit harder than the physics here. And so here's how we calculate our torques. And of course, once we know that, we can then do the rest of this problem, which this one would say that Fx then is t times cosine of 60 degrees, and we just did the tension, so let me multiply it by cosine of 60 degrees, and Fx is 171 newtons, whereas this one here is saying Fy is 980 newtons minus t sine 60 degrees. Now I'll put the numbers in here, but let's just make sure that makes physical sense to us. Here's what you're saying. You're saying this rod does have an upward component. Sure. What is it? Well, the 980 is what's pulling it down. And then you subtract off how much this one is pulling up to be left over with how much that one is pulling up. So 980 minus 343 times the 60 sine of 60 degrees, and that comes out to be 683 newtons. And so now I've answered the question: what are the components and what is the tension? Now I suppose I could have asked this a little bit further and said, well, what would have been the magnitude and direction? Now they didn't actually ask it, but let me go ahead and do that. What the magnitude would be Fx squared plus Fy squared, square root. And so here's my 171 in the x direction, my 683 in the y direction. And so 171 squared plus 683 squared equals, and the square root of all of that is 704 newtons. And so the total force is 704 newtons. That's how strong that pin has to be. So we better make sure we make it thick enough and big enough out of whatever material it is to handle 704 newtons. Otherwise it's going to break. Okay. Which, by the way, we won't worry about the material breaking. That won't be part of our chapter. But that will be part of next semester. That's what, you know, the statics class will do. They'll say, okay, let's start here. How much force is it? And then we'll say, okay, this is made out of a steel beam. Then how thick does the steel beam have to be, or the minimum thickness, in order to handle the 700? We could have also asked for the angle. This could be some angle from the horizontal. So the vertical piece is 683 and the horizontal piece is 171. So tangent of that angle is 683 over 171. And so we can find that angle there, inverse tangent of 683 divided by 171, and we come up with about 76 degrees. So the force coming from that pin in there is really mostly up. Kind of makes sense. It's pushing mostly up to counter all the weight here, but enough also to counter the force pushing inward as that cable's trying to push it into the wall. It's got to push back. And so the two are balanced just enough to make everything happen and to keep it from rotating. So it's how our forces come into play. Whereas C goes one step further. It says, now, if the wire can withstand a maximum tension of 900 newtons, will this break the cable? Well, apparently not. It only needs 343. It can handle up to 900 before the cable breaks. Okay, so now the bear can go further out. What happens to the tension in the cable? Right, and hopefully you can see that this X would start to increase, giving you more negative torque here. These guys wouldn't change, but in order to counterbalance that, you need a larger positive torque, so the tension in the cable increases. Now, of course, if the tension in the cable increases, then these also change. But I don't think they're going to go that far to look on those. They just said, look, this is going to increase. So, here's the question. How far does the bear go out before the cable breaks? And so that's what it says. So what is the maximum distance the bear can walk out? So in other words, when the bear's only at 1 meter, it doesn't break. And it gets to 2 meters, it still doesn't break. 3 probably doesn't break. I don't know. But at some point, before it gets to the 6 meters, it breaks. That's why earlier I called this the bear trap. Because essentially what's going to happen is we can put a little net down here. And say what's going to happen is the bear's going to get out to here, cable's going to break, and the whole thing, this is going to fall down, and the bear falls in there. And we still have food to catch another bear, so we can swing it back up here and doesn't even get the food, and ready for the next bear. So there's our bear trap. But that's the question, how far? So what would change here? What would you do different to answer C? How far out can the bear go? Yeah, so the unknown is X, right? But the tension is the 900, the maximum. In other words, that's the question. Where is the position of the bear when the tension gets up to 900? And hopefully it'll be something less than 6 meters. If it turns out to be 7 or 8 or 9 meters, that tells me the bear gets all the way out to 6 meters before the cable breaks. So, but I've done this one in the past, and I know it breaks somewhere before 6 meters. I don't remember where, but I know it breaks before 6 meters.
If you wanted to find where the pin would break, would you use the Y, or would you use the combo? Oh
yeah, good. Well, you're going to have to use the combo, assuming yeah. So then you can put in good point. You can put in the tension and find out. Now, if the cable goes up to 900, then you could figure out what the tension on the pin has to be. And you better make sure the pin can handle at least that much. Otherwise, the pin will break before the cable breaks. Yeah. So
it would be the combo of it.
Yeah. Good point. But again, anything that has to do with the strength of the material itself is a great question. It's just not one we're trying to answer this chapter and this semester. That's for next fall. Okay, so here is C, and let's run through this same equation. So as I go to calculate the torque on the z-axis about the same point A, I would say it is an X, there's the unknown distance, 700 negative direction, sine of 90 degrees. And so that's my first term repeated. But now instead of putting a 1, I'll put the actual X. Whereas the beam itself and the food, if you don't mind, I will just put a negative 600 Newton per meters there. That's the distance of 3 times a force of 200. And then the basket of food minus the 480 Newton meters is the torque we get from the basket of the food. Again, for the same reason. And now we get the positive 6 meters times the did I say 900? Mm-hmm. Pretty sure it's 900. 900, and then the sine of 60 degrees. So that all has to come out to be 0. So the unknown is the x. Let me just double check. That's what was given in the problem, that the cable can withstand. If the wire can withstand a maximum tension of 900, so I'm setting it to its maximum. I'm saying, in other words, what position does the bear get to so that the tension gets up to its 900 and then breaks? Okay. And so now we got a little bit of arithmetic to do, but this would be x times 700. When I move it over to that side, that's your 1080 again. This is, ooh, I don't know what that is. I need a calculator for that one. This is the 6 times the 900 times the sine of 60 degrees. So that's 4,676 there. So I'll subtract the 480, subtract the 600, and this is 3,597 Newton meters there. This 700 newtons will cancel off, and we are then dividing by 700, and we are at 5.14 meters. So close, but not quite enough here. So about little past 5 meters, the cable's going to break. And like I said, bear's going to fall into the bear trap. All right, well, hopefully that first one there makes sense. And everything else is exactly those same lines. So let's see if we can go maybe a little bit quicker here, but showing you the same thing. It just may be different scenarios here. So we'll start off with 41 on again and say, okay, let's look at this one. This happens to be a crane. Here it says a crane of mass 3,000 newtons supports a load of 10,000 kilograms. Oh no, I'm sorry, the crane has a mass of 3,000 kilograms and supports a load of 10,000 kilograms as shown in the figure. The crane is designed to pivot around a frictionless pin A, and it rests against a smooth support B, as shown in the picture. Well, maybe I better show you the picture, especially since we don't live in an area that's got a lot of cranes mounted on the side of buildings. We just don't have tall buildings in our area. But if you lived in a major city where they were building, you would see that they'll often put a crane or mount it on the side of the building so the trucks can pull up and then they can reach out and grab the material and start building the tall building. And so it looks something like this. This is what you might call the superstructure of it. There's a little pulley here on the end so that the cable can come down, and they're saying it's designed to lift up 10,000 kilograms at a time. The structure itself has a bunch of I-beams inside here. Oh, maybe I'll do something like that. Okay. Now their picture's a little bit nicer, in fact, that it's wide and narrows in, because in the picture they say it does have a center of mass right about here. In other words, the center of mass is not the the center of it. It's not a nice uniform object. It's got much more material back here than out there. And what they show then is this is the gravitational force related to the 3,000 kilograms that make up the structure of the crane. And they say then that this distance is 2 meters straight out, although they're not saying the center of mass is straight out, but they are saying along this line. Maybe I should put the center of mass down there. So we don't know that it's at the same height, but they are saying if you take the pin and go out straight on the x-axis horizontally, you get to the 2 meters. That's where the center of mass is, because it's the distance out to your weight that is 6 meters. And so again, the center of mass is not in the center of the crane. It's not 3 meters out. So it's closer to the building. And so they call this point A and they call this point B, and what they said is it's real smooth right there, and that this is 1 meter. And so you've got a 1 meter distance between point A and point B. So I'll start again in 41, because again, I can't overemphasize, probably the most important part of this is a good physical understanding of what's going on. You won't understand why certain steps are made if you don't understand the picture, or if it's the case of a test, you won't know what steps to make if you're not, seeing that physical picture here. But so a crane of mass 3,000 kilograms supports a load of 10,000 kilograms as shown in the figure. The crane can pivot around a frictionless axis at A, and it rests against a smooth support B. Find the reactionary forces at A and B. All right, so I'll draw the free body diagram in a minute. But before I leave the picture here, I'm going to just grab my blue pen here and say, all right, do we know anything about these forces? Say at A. Do we know the direction is this way? Do we know it's horizontal? Yeah, we really don't. It's not a cable or a rope. It's not something flexible. So maybe we should label it as a force in the x direction and a force in the y direction. Fair enough? Let's look at B though. B is really an important step here. It's the reason they called it a smooth surface. Look at point B here. What are they really trying to say here? Yeah, they're trying to say is it's just a smooth thing. In other words, the crane comes down and hits point B like this. So if something makes contact and it's nice and smooth, what direction is the force on this contact? So the crane would be pushing that way on the wall then would be pushing that way. And only that way. Would it be pushing up or down? No, because that would take some roughness, right? That would take the rigidness of it. It would have to be bolted together for that to happen. And so they're trying to help you out here by saying, look, the force at B, and I'll just label it force B, has got to be all horizontal. It's not also up. Which is probably good, because then that means we have 3 unknowns and we're going to have 3 equations. Some of the force is x, some of the force is y, some of the torques, right? And so there's our 3 equations, okay? In fact, if I was real clever, I'll leave it alone like this, but if I was really clever, I could even stop here and think that this doesn't seem to make a whole lot of sense. How could both of these be in that direction? 2 forces that way? There's nothing that way. What would happen to this crane? Yeah, there's no way you can have both of these forces that way. Because all that does is push the crane that way. So what does that say about these? Yeah, one's got to be backwards. If this one is forward, this one's got to be backwards. So we've already argued this one is forward or to the right, so this one's got to be to the left. And maybe it makes sense. Imagine this. Imagine calculating the torque around point B. I mean, watch the pivot here. If there was a pin here, now I know there's not a pin at point B, but to think it through, if there was a pin at point B, if it could pivot here, this thing would be making it pivot in a clockwise direction. Fair enough? And so would the weight of the crane. So both the weight of what they call the load, what you're lifting up, and the weight of the crane, both of these are making the crane rotate towards the ground, rotate in a clockwise direction. So what would have to happen is this has to do what? It's got to pull back that way, trying to make it rotate in a positive direction. So for those two reasons, I probably should draw f of x that way. But let's just say I don't recognize that. And I go through all the math. Will I do it wrong? No, what will happen here? Yeah, I'll just get f of x is negative. In other words, f of x is negative of the direction I labeled. So let's do it that way. Let's show you that you don't really need to be that particular about it. It's just a number. Solve it. And if it comes out to be a negative number, that means it's in the negative direction. Okay? So you can treat it as one direction, and when you're all said and done, if you get the opposite of that, then okay, that's the way it works out. It's opposite to the direction I chose. And so I'm going to leave it alone and just draw my free body diagram in that direction, but then expect it to really come out to be a negative number to emphasize to you. So I will start off, like all these problems, with a free body diagram, which I essentially have. So here's the crane. Something like that. And so I have a force here. I have a force here. I have an Fx and an Fy. And I have an Fb. This is 3,000 times 9.8. This is 10,000 times 9.8. And then we can do the same thing we did before. Now, maybe it's worth mentioning it, but I think you got the ideas. Do we know the direction of the force on the crane from this cable? Yeah, because it is a cable, because it is flexible. We know it's in the direction of the cable, and so it is straight down. In addition to that, we know it's equal to the weight of that, because if we did the free body diagram with this one, it would balance off. And that's what we did for the basket of food. Okay? So for those same logic, let me not do it again here, but let me write out some of the forces in the x direction, some of the forces in the y direction, some of the torques along a z-axis. All of those have to be 0. Okay? And that's what this chapter is all about. That's why it's a short chapter. It's a little introduction to statics, a little get ready for next semester, where many of you will take our statics class, or some? I don't know. Do you guys already know? Who's taking the statics next fall? So, all right. I don't know about many, but some of you. So, all right. Which I guess there's many reasons you may not. One of them may be you are transferring. One of them may be that you're not going into engineering, or does all the engineering have to take statics?
No.
No.
Not electrical.
Not electrical? That kind of makes sense. So not electrical, and probably not chemical. And yeah, probably not nuclear or any of the other ones. Yeah. But probably mechanical and civil. Those are probably the two subgroups.
Wait, what's engineering 116?
116 is dynamics. Yeah, yeah. So 115 is next fall, where you do statics, where everything comes out to be 0. Then you follow it the next semester with not equal to 0, dynamics. And so now you have things actually moving. So. All right, so back to our problem. Our problem is static, and we've got to add these up here. And so now let's look at the free body diagram. The x direction is the one we were mentioning earlier. This would be the force in the x direction, and this would be the force also in the x direction. Those are the two that have to add up to 0. That's what I was saying. One of those has to be positive, and one of those has to be negative. I mean, you can see that in the math right there. Okay? In the y direction, you can see that you have a force in the y direction pushing up, and you have a negative 3,000 times 9.8, and then a negative 10,000 times 9.8, and that has to be 0 also. So there's our second equation. And actually, that's kind of a nice one. That's one equation, one unknown. Right? So shall I just pause and actually solve this for Fy as long as we're here? I haven't even written out the third equation yet. But I'll do that one right there, because that's 13,000 times 9.8. And so that is 127,400 newtons. Because this is kilograms, meters per second squared. Kilograms, meters per second squared. So that's how many newtons there it is. And I'm hoping those are the more obvious ones. The one that is harder this unit, the stuff we learned in chapter 10, was torque. So 10, 11, and 12 all have to do with torque. And so there it is again. So I need to ask, the sum of torques about what axis? Any axis. So pick one that's going to make this a little bit easier to do. What axis do you want to pick? Yeah, I would encourage you to go with A. Why? Yeah, how much torque do you get from Fx and Fy? 0. And so 2 of our 3 unknowns are completely gone from our equation, and we're going to have an equation with only one unknown, Fb. And so we can solve this equation for Fb, and then once we know it up there, we can get Fx, and we already did Fy, and we're done with the problem. Okay? So let's write it out as measured from point A. So the torques on the z-axis as measured from the point A. All right, well, let me start with the center of mass. The center of mass, 1, or any torque, is R cross F, right? Which is RF sine of the angle between them. This one's going to make you think a little bit. This is why I grabbed this one. It might be easier than it looks, but we really don't know what R is. Isn't R the distance from A to the center of mass? Now what we know is the horizontal distance is 2. But since we don't know how far down it is, we really don't know R. And then likewise, we don't know the angle. But we saw this with our rotational motion. Our angular momentum. If you had something that looked like this, and your force is straight down, and there's the angle between them. If this is R, you don't know what R is, but if you also don't know what phi is, what is R sine phi?
R perpendicular.
Yeah, it's that, what we often call the perpendicular distance. And so, a nice way to calculate this is to remember that fact, that even though you don't know R and you don't know phi, the two together you do know. And that's the perpendicular distance. And that's what they have told me here. They have told me the perpendicular distance is 2 meters. So we know that one. Okay? And so now, when I go to calculate the torque, I can think of it as R perpendicular, which is 2 meters, times a force of 3,000 kilograms times 9.8 meters per second squared. So there's the perpendicular distance, and there is the force. Okay? So sometimes that's convenient, and sometimes that's convenient. And sometimes that matrix is convenient. Okay? Mostly, though, we have done this, and now we're doing a little more of this. And we'll probably wait till next semester to do a lot of this. All right, so there's our torque. Now we should probably ask, positive number or negative number? Yeah, of course, part of that depends on what you call the positive and negative direction. But sticking to tradition, this, if you imagine the pin here, this force of gravity would rotate it in a clockwise direction. And so that's a negative rotation. Or taking your right hand, putting your fingers towards R and closing them towards F gives me a thumb into the board, negative direction. So sticking to the tradition, I'd call that a negative torque. So I've done its magnitude and then I've done its direction. Okay, and so there's my torque. And likewise, the same thing can be said for this heavy load out here. Again, I really don't know what R is. But if I come over here and draw a picture again, this is my R. This is my F. This is the angle between them. And although I don't know what R is or the sine of phi, R and sine phi together make R perpendicular. So using this one again instead of that one would tell me that the perpendicular distance is 6 meters. So there's my 6 meters. That's the perpendicular distance. The force is 10,000 kilograms times 9.8 meters per second squared. And again, what direction is it? It's a negative rotation. So both of these are rotated in the same direction, in a clockwise direction. So there's my rotation, clockwise. Anything else? Yeah, B. So then I've got to do the torque here. And again, I'll use this same equation. The perpendicular distance now is 1 meter. And so I've got 1 meter going down, and I've got the force at B, and that, if you look closely, is a positive torque. It is pushing it in a counterclockwise direction. And so this one is pushing that way, counterclockwise direction. And right hand rule, but I guess I'd put my fingers in the direction of R, close towards B, and then I'd give my thumb out of the board, yeah.
Any of the forces that we did are perpendicular for weren't in the direction that they are in, so that, like, let's say FB was somehow pointing downwards, but you already, with that effect, because you already eliminated the use of the sine phi in getting R perpendicular.
Oh, I see what you're saying. No. Okay, let's draw that one. And I drew the first two, but this one, okay, if I drew down to here, there's R, and there is F, okay, then, well, that's already perpendicular, so that's not a very good picture.
But if somehow F was, let's say, 45 degrees.
Oh, okay. Then, I got you. I see your question. Okay, so it would look something more like this. So here is R, but now F is something like that, right? Okay, so let me kind of make a set of triangles out of this. I guess there's two ways we can look at it. If this is phi and this is R, then this right here is actually R sine phi. And that I don't know if this is going to be the 1 meter. So when we say perpendicular distance, we really mean the distance perpendicular to the line of the force, what we often call the line of action. So I don't think this would be a good choice, but I would encourage you to do this then. Let's do this. Why don't we look at this triangle made up by F? Okay, because I'll extend this kind of down here. This is phi, and so this right here is F sine phi. Well, or F perpendicular. So another way of looking at this is to say R times F perpendicular would be the same as R perpendicular F. And so the case you bring up probably would be better be done this way than this one. And I suppose you would also see that if we broke it down into its components and did the determinant of of the matrix, which we really haven't done much this semester, but we'll do a lot next semester. Yeah. Okay, so let's see. So I'm calculating this, yeah, and then the unknown here is FB. So FB equals, and so let me calculate this torque here. This is 2 times 3,000 times 9.8. This one is 6 times 10,000 times 9.8. And put the two together, although they're negative, I'll move to this side of the equation, they're positive. Divide by 1, and I get a force of 646,800 newtons. So there's the force in B. And it's a big force, but hopefully it doesn't surprise you, because first of all, we're already lifting two large forces. I mean, this is 13,000 right there, multiplied by roughly 10. And the downward force is already close to 130,000. I guess we calculated it here. So the downward force is already 127,000, but this is much bigger than that. But again, maybe not too much of a surprise, because what we have to do is get the same amount of torque. So we only have a distance of 1 meter, whereas these distances are bigger. And so you got to have a much larger force down here to counterbalance the rotation that comes from these smaller forces. So big force, short distance matches small force at big distance. And of course, once we have that, we can finish the problem by coming up here and saying then Fx is the negative of Fb, which then is a negative 646,800 newtons. So a very large force there in that little pin. And that's a consequence we get of only having a short distance right there. And so for better or worse, that's what we have to. Yeah, so obviously you need to make sure the building can support all this, or that the supporting pin can, otherwise it will come crashing down here. And there was one semester where, interesting enough, the night before, and it could have been just as last semester, but I'm thinking it might have been actually a whole year ago, but it was, the news the night before. I just happened to have a crane in New York City on the 12th floor that came crashing down because of exactly this problem. It was either wasn't strong enough as needed to lift that weight, or somebody put too much on, but either way it comes crashing down, and fortunately nobody got hurt, but it easily could if you're 12 stories up in the side of a building and people walking. About 1,000. So there's about, you're lifting about 5 tons, yeah. So, which I guess isn't really that much material. It sounds like a lot, but 5 tons, I mean, it's like lifting an elephant. So, yeah, well, yeah, right. But when you're lifting a lot of bricks or a lot of rebar or a lot of concrete, it just isn't that much. Well, the concrete they probably pump up with so. Well, again, here's kind of a fun one to do. 42. 42 kind of emphasizes the same thing. And again, I'm hoping that you'll see all day today, as well as in the lab, that it's really the same problem again and again and again. The sum of the forces is 0 in the x direction, the sum of the forces in the y direction equals 0, and the sum of the torques is 0. So we're just applying it to a very limited, very special case. That's why I said short chapter. And this one, they say, let's look at somebody bending over to pick something up, but they don't bend their knees. And maybe you've heard that, say, if you're going to lift something up, lift it with your legs, so bend your knees. What happens if you just bend at the waist and then you lift up? And it's really easy to hurt your back. Why? Well, yeah, you'll see it in here. Watch, let's go through some numbers here. And so they say, let's model the person's back, and I'll kind of shorten it. They got a lot of words there, but in the interest of time, and I want you to see at least 2 more here, let me kind of give you the short picture of it. What they do is they say, let's pretend somebody bends kind of straight over, and so their back is straight. In other words, this is their hips, and so their legs look something like this. Oh boy. There we go. So there's their legs to kind of give you the idea. And I guess their head is over here somewhere, and their arms are dangling down here, lifting something up. But they definitely overly simplify the motion of the human body by just saying, let's just treat this as a long rod where the person has just bent right here at the hips, and they go down to lift something up here. Okay? So let me draw the rod again. So they draw the rod here and say, all right, here's this person bending over, and we'll just say that the upper part of the body is about uniform, so the torso. So from the shoulders to the hips, maybe has a uniform distribution. So right in the middle is a center of mass, and it is about 350 newtons. I guess that seems reasonable. What's that? 35 kilograms, a little over 70 pounds. Okay, so from here to here is 70 pounds or ish. Okay, so there's their body part. But they're lifting something up, and it's not much. And they say they're lifting something up that is 200 newtons, which is about, 20 kilograms? What's that? About 44 pounds? Yeah, 20 kilograms. That's the dog food I buy always says 20 kilograms. So it's a big bag of dog food, all right. So somebody, in Costco, picking up a bag of dog food, okay? Okay, but it's a terrible way to lift it up, and that's what they want you to see here. And so there's the person lifting it up here. Those aren't the only forces, though. What other forces would be on this person's back? Well, there's this little ball joint right in there, right? I mean, that's what's making you kind of pivot here. Okay, and so just like we've done back here for the crane and the bear trap, there would be some force here in the ball joint, and here, okay. And I don't think they're really worried about that. That's pretty strong. But if this is a big number, you're actually pushing on the spine. And there's the problem. Your spine is made out of vertebrae, and between your vertebrae is soft cartilage. And if you push really hard, what's going to happen? Yeah, you're going to deform that cartilage, and if it pops all the way out, I guess you slip a disc, because that's a disc. It either comes out, or you pinch it, and it just kind of splits it in two, and anyway, all kinds of pain that can result from that, because then it pinches on that spinal cord here. So that's the idea. Now, it's not the only thing. There's one more thing. How does your body lift up? I mean, as I bend over and go to lift back up, what's pulling me up? Well, I guess I got a bunch of muscles here with a bunch of tendons, and they show it in this picture as only one tendon. So they definitely overly simplified here, but they got it like one cable that is pulling up, and they said here's really what makes this a dangerous way of lifting something up is that angle can be really small. And so if you pivot here at your hip, there's not much height here for these tendons. And so the height here where these tendons are hooked are really small, and there's only a 12 degrees. So as your body is pulling you up, what is most of the tension doing here? Yeah, most of it is compressing the spine together. Very little of it is lifting it up. So if you're lifting up only 200 newtons, then this force horizontally can be much greater than 200. And so we'll solve that. We'll see how much greater it is, and we'll see how much force really your back has to support, even though you're only picking up a 44-pound bag of dog food here. What does your back have to do? And so that's the idea here. What is that? Now, here's the part I wanted to make sure you saw, besides just the human dynamics of it, is the fact that they don't really say how big the person is. They just say the upper body dorsal has a length L, and that the tendons are attached 2/3 of the way up the back. Okay. 2/3 muscles. Erectile spinous muscles attached to both ends, 12 degrees. Model, can you do? Thought they said 2/3. I don't even see it in here. Is attached to the point 2/3 of the way up the spine. Yeah. Okay. So there's the problem, and like I said, I kind of overly simplified it rather than reading the whole detail, because they talk more about the human body than they say let's take a simpler model there. But I think you got this. This would be a simpler model of it. And again, here's the question. Just like the other problems, could you solve this for the tension and the components of the forces at the pivot point? Sure. So let's write them out. So some of the forces in the x direction. Well, there's the fx. And there's minus t sine of 12 degrees. And that's, like I said, that 12 degrees is the real catcher here. This one is pulling back, that one is pulling up. Equals, good question. That would be cosine, thank you. Cosine, that would have to be 0. Some of the forces in the y direction would be Fy is pulling up, and then the sine of 12 degrees is the one pulling up there from the tension, and pulling down is minus 350, and also pulling down is minus 200. So down, down, up, and up, equal and opposite, and that one has to be 0. And then finally, the third one is the torques have to come out to be 0. And again, torque around what axis? Well, the answer is any axis, right? And so we're going to do a lab on it and make you do one axis and then try the other axis. So be clever here and pick the one that will be the best advantage to you. All right? And again, the one that's probably the best advantage is right here. Why? Yeah, how much torque do you get from these two? 0, and they're going to fall out of the equation. So the only thing left in the equation is the t. And so with that in mind, we can then calculate the torque from just the weight of the upper dorsal. Its distance is L over 2. Its magnitude is 350. Its direction is negative. The weight of the bag of dog food is a distance L. It's got a weight of 200, and it also is in the negative direction. And notice for both of these, I used this perpendicular distance. Whereas now that I've got an angle that's not so easy to deal with, but I know it, I think I'll jump back to that formula and calculate the torque there. So the torque there would be the distance, which is 2/3 L, times t, times the sine of 12 degrees, and that would be in the positive direction. And so this one is a positive rotation, and the other two are a negative rotation. And that all needs to come out to be 0. And fortunately, if you look carefully, I don't need to know L. Now that was looking a little concerning to me. It was like, whoa, I don't know L. But I have an L, an L, and an L. So if we divide everything by L, the L cancels out of the equation, since this is still equal to 0 over there. So I don't need an OL. So it's going to work the same whether this be a tall person or a short person here. And so now I can calculate this. So I've got half of 350. What's that? 175, and then 200. So that together is 375 moved over to here. So plus 375 from those two. Then I can divide that by 2/3, and then I can divide that by the sine of 12 degrees, and that's the tension in the back. But you can see then the tension is not just the weights you're holding, but a combination of distances and angles. And so these small numbers down here really make this into a very large number. And so what do we come up with? 375 divided by 2/3 divided by sine of 12 degrees. And we're looking at 2705 newtons for the amount of tension there in the back. Now remember, we're only lifting up 200. Right? This is over 10 times as much. And then if we're trying to solve this for how much then is the hips, the ball joint are pushing on here, then this becomes Fx equals tension times cosine of 12 degrees. And so times cosine of 12 degrees comes out to be 2646. And again, much greater than the simple, 20 kilograms you're lifting up. Many times. Let's see, that's newtons. If I divide by 9.8, that's kilograms times 2.2. So that's equivalent of 600 pounds. So that's the same as, standing straight up and somebody dropping 600 pounds on your head. So it's a big difference then in how much is on your spine and how much is compressing your spine, which, like I said, is, as they say, not a good way to be lifting something up. And then hopefully you can see why with the angle of there being the 12 degrees. Well, how about I try number 45 and more if time allows, but at least we get this many done, and that's kind of what I was hoping for. Oh yeah, we should have time for another one. But 45 says this. Here's this big file cabinet that we're going to slide here. It says, a force is exerted on a uniformly rectangular cabinet weighing 400 newtons as shown in the figure. All right, so they've got this cabinet. And they do say the cabinet weighs 400 newtons, but they did more than that, and I'm sure why when they say this. A force is exerted on a uniform rectangular cabinet weighing 400 newtons. So the weight is 400 newtons, but where's the center of mass? Yeah, right in the center of it. So right here, I'm going to put 400 newtons. So halfway up and half of its width. They say the force is applied somewhere on the side. And so there's the force. So here's this cabinet. Maybe it has a handle on it, and you reach out to grab the cabinet, and now maybe you're going to say pull it. So you pull it. And so in this case, it's not a straight horizontal pull. You're pulling up at an angle, as they show there. And in the diagram, they show that this place that you apply the force is a distance h above the ground, and the angle is 37 degrees. Now the cabinet itself is 1 meter high and 60 centimeters wide. So there's the dimensions of the cabinet. A force exerted on a uniform rectangular cabinet weighing 400 newtons is shown in the figure. A. The cabinet then slides with a constant speed when the force F is 200 newtons and the height is 0.4 meters. Find the coefficient of kinetic friction and the position of the resulting normal force. Now, maybe I should put A here and do free body diagram, which I guess I kind of have done there. There is 400 newtons. And I would say that the distance that this 400 newtons is being applied from this corner is halfway. That's what we had argued about the center of mass. If it's 60 centimeters wide, there is the distance away. Now also, what they're saying here is that as somebody pulls it with a force of 200 newtons, at that angle of 37 degrees, at a height of 0.4 meters, see if I read that right, the cabinet slides with a constant speed when a force of 200 newtons and a height of 0.4. Find the coefficient of kinetic friction and the position of the resulting normal force. In other words, am I done with my free body diagram? No. What forces am I missing? Friction and normal, right? So this is just the obvious ones. The obvious ones are somebody reaches out and pulls on it. Another obvious one is the force of gravity. But in addition to that, as it slides across to now, there is the force of kinetic friction. And then there's also the normal force. And see, this is something we haven't had to deal with yet because we haven't done torques. Where is the normal force? Does it matter? Yeah, not until now did it matter. Before we just said, well, it was an upward force, and we just drew it upward. But doesn't the position of the normal change the torque? All right, so this upward force is where? I mean, maybe I'll put it here, where this distance is x, away from that right-hand corner. And I think you can start to see that if we kind of look at this corner right here, what we have is we would have the force from who's ever pulling on this handle, that's tending to rotate it over like this, right? But gravity here is tending to rotating it back the other way. Now, if gravity is rotating it more back than this is forward, then wouldn't we need the normal force here? Mm-hmm. And depending on how much more, because if the gravitational force is just a little bit more, then we don't need much torque. So how could we get less torque but still the same amount of normal force? Yeah, if the torque was closer in here, right? And so it doesn't really matter where the let me say this right. The normal force is still going to be the same amount. It's just where it is needed in order to get the torques right. And I think you'll see that here in the equation. And so let me just double check. Did I get all the forces? We got somebody pulling on it. We got the ground, which rubs on it, which has friction and normal. Okay, good. And then the force of gravity. And so as I go to calculate this, I would say the sum of the forces in the x direction equal, no wait, 0, but it's moving this time. So is it still 0? B. I'll read it again here. I'm sorry, A. A cabinet slides at a constant speed. So what does constant speed mean? 0 acceleration. All right, so yes, it is 0. So is it moving? Yes. Probably shouldn't call this static equilibrium. Since it's moving, it's more like a dynamic equilibrium. Okay, fair enough. But not worrying about the semantics. It's still got to come out to be 0, right? The sum of the forces in the x direction have to be 0. Sum of the forces in the y direction have to be 0. And I'm going to assume in this problem that it, doesn't rotate either as this person. So in other words, this person is pulling this cabinet across the floor like this. And it goes at a constant horizontal speed. It does not rotate. So that comes out to be 0 also. So no angular acceleration and no linear acceleration, although it is moving. Okay? So in that sense, it still fits into this chapter. It just maybe doesn't fit under the word static. It fits in the word as dynamic equilibrium, but still equilibrium. All right, but again, add up the forces. So let's add up the forces in the x direction. Well, in the x direction, you can kind of see that your hand is pulling it with 200 newtons cosine of 37 degrees. So that is the x component of that one. Gravity has no x component, normal has no x, but then minus the force of friction, that has to give you your 0. Now, were we trying to find the force of friction or the coefficient? Which was it? The cabinet. Find the coefficient of kinetic friction. All right. So, solving this one would say that the force of friction is 200 newtons times cosine of 37. But the coefficient of friction would then be, the kinetic friction would be the coefficient times the normal. And so I can't really get the coefficient until I also get the normal. All right, so I'm kind of stuck here in the x direction. Let's go on to the y direction then. In the y direction, it looks like I have a 200 sine of 37 degrees lifting up. I also have a normal force lifting up, and then I have a 400 pushing down. That should allow me to get the normal force. So the normal force would be the 400 minus 200 sine of 37 degrees. So that I can solve for. And so it looks like I can do A without even talking about torques yet. So 400 minus 200 times sine of 37. And this is then 280 newtons for the normal force. And so once I get that, I can get the coefficient by taking 200 over 280 and multiplying it by cosine of 37. So 200 divided by my last answer times cosine of 37 is 0.57. All right, so there's the coefficient of friction. Fairly high coefficient if you remember from our chapter 5, but maybe not a surprise. Cabinet, really not designed to be sliding, so maybe it's on carpet too, so it's going to be hard to move. But once we get it where we want it, it'll stay there. That's good. All right. So there is the first part. What's the coefficient of friction? Oh no. Find the coefficient of kinetic friction and, oh, I'm not done, the position of the resulting normal force. So I found the value of the normal force, but I haven't found the position of it. And of course, to do position means I've got to do torque. That's the only one where position comes into play. And so that's what I was saying here, is until we got to this part of the material, this part of the semester, this is the stuff we would have done in chapter 5, and we would have said that is the normal force. End of story. We wouldn't have said where it is, but now we have to also say where it is. And that's this one here about the torques having to come out to be 0. And of course, to calculate a torque, you have to say about what axis. And I would suggest you use the one that is to the best of your advantage. We could debate which one is to the best of our advantage on this one. But I'm taking this bottom corner, as I really like it. What it does say is how much torque do you get from friction? Yeah, 0, right? And so it kind of goes away. Although that's really not needed because I just found it. So I'm not so sure that that's the best choice. But the other things that are left are the force from my hand, which I know, the force from the gravity, which I know, and then the normal force, which I would also like to find here. So I do think that's kind of the best of the choices. So going through this, why don't we do the torque from the normal force? The distance out is x, and the normal force is n, which we do know its value. We'll put into 80. And if you look closely at it, it is a distance and an x, so that tends to rotate it in a negative direction. Right? The other one we know is the force of gravity. And then again, let's use the perpendicular distance. So the perpendicular distance is our 30 centimeters. So the distance is 0.3 meters. Its magnitude is 400. Actually, I'm going to put a 280 over the n here. So I know that number. It's the x that hopefully will be the only unknown here. Okay? And then I should look which way its torque is. And then maybe you can see here, if you see it, it's going to tend to make the cabinet rotate this way. If you put your finger here and it wants to make it spin in a positive direction.
If we're doing it around that point at the end.
Yeah, so let me call this A. And so I've got to calculate the torque around A. Again, you can only calculate the torque as measured from what point? And I don't want to imply that that has to be the point. It could be any point. You could have picked this side of the equation. You could have picked the center. You know, there's all kinds of things. Could have picked.
Force, right where the force of gravity is, or mg, where mg is it the same place as?
I don't know where the normal force is. That's the question. Where is the normal force? So it's some distance out. If it turned out to be 30 centimeters, then it's directly below the center of it. If it's further out here, it means I needed quite a bit of torque from the normal force, which means this one's not really rotating it much compared to the force of gravity. That's why it needed to be way out here. The other one might be a little bit harder. In fact, it goes to your question. How do you want to calculate the torque here? You could break this force down into its components, right? And say, this force would have this much in that direction, and then you would have R perpendicular times that force, and then the vertical one would not give you any torque. And I kind of like that one the best. But you could just as easily call this R and this F, and then do sine of 90 plus 37. Whichever you like. But I'm thinking it might be best to call this 200 times cosine of 37 degrees and say, okay, now the torque I get from this person who's pulling on it has a magnitude of 200 cosine of 37 degrees. That's how much force is horizontal. And they are a distance of 0.4 meters away. And again, if you can imagine this point being stationary, this person is tending to rotate it the same as the normal force, the negative direction. So the normal force and the person's hand are rotating it one way, gravity's rotating it the other way, and the only unknown is x, and so we should be able to solve this for x. Where is the position of this normal force? And maybe I'll get the calculator here. This, I guess, is a 0.0 Newton meters there. This is an 800 with a decimal Newton meters, times cosine. Well, maybe I just better work that one out. 0.4 times 200 times cosine of 37. So this is a negative 63.9 Newton meters. So I'll take that one, which is negative. Okay, so that's negative. I will add it to 1200 and move the other one to the other side. So when I move, this is equal to 0. So I move that over to there. I get x times normal equals 56.1 Newton meters. And so then finally x divided by 280 comes out to be 0.20 meters, or about 20 centimeters. So it's not really in the position like my picture shows it. It's actually over here already. So it's this side of the center line. And so that's where that normal force would have to be. If the normal force was not there, if it was further out, that would tend to make it tip over. If it was further in, it would tend to make it go back. So the normal force, its position adjusts itself so that our torques are balanced, and yet we still have an upward force needed to balance all the gravitational force pushing it down. And so once you understand all that, then we can go into B, which then B says, taking the force F to be larger at 300 newtons, find the value of H for which the cabinet just begins to tip. In other words, what would begin to happen if, say, you pushed with more than 200, which in this case is 300. Let's just leave H alone for a moment. What's going to happen? Yeah, you start increasing this force from 200 up to 300. That's more negative torque, right? What's making it rotate the other way doesn't change, so what has to change is less torque here. So what happens is the normal force shifts positions. And to get less, that means we would move closer this way. So instead of having a normal force at position of 20, the normal force will now scoot over and be something less, because now you're pulling it less. Okay? And it can only do that for so long. If you start pulling more and more and more, X can get less and less and less, but once it gets to 0, what happens? You can't do anything, it's just going to tip, right? So you pull this thing too hard, it tips. You want it to slide, not tip. So you don't want to pull it too much. Now, if it does start to tip though, the other thing you can do is lower your torque. How could you lower your torque? By pulling it further down here. And that's what they said, find H. In other words, pull it harder at 300, but pull it at a lower H so that it just begins to tip. So you want to pull it hard, you want to pull it low so that you can slide it across without getting it to tip. So again, going through that same math, we want the sum of the torques around the z-axis as measured by point A to be 0. And so let's drop off this point 4 and now call it H. And we can really go through the same thing. We want it to be just at this point where it's going to tip. Now if it's just going to be tipping, then we know that the normal force has moved closer and closer and closer and closer and closer and can't get any closer. So what's the value of X? 0. So we get no torque from the normal force. The normal force has moved all the way over to be right under that corner. And it's about ready to tip. Okay, so we get nothing from that part. Now, the thing from keeping it from tipping it is still this term here, that 0.3 meters and the 400 newtons, and it's in the positive direction. So this is still keeping it from tipping. It's over here now that my hand, as I pull on it, is at some height h. There's the unknown. Right here. And I'm now pulling it, what they say, 300. And the component that is pulling it is the cosine of 37. So you can see I have an equation that has an h. And we're out of time, so I'll stop there and let you solve that for h. But that would just tell me where the height is. Lower than that, everything would be fine. Higher than that, it's gonna tip over there. All right, well, we'll work on these in lab too. So.